Hi, I'm Mike, and I have gotten interested recently in 3D printed musical instruments. And I started printing some things on Thingiverse, and the quality wasn't really high. So I'm looking for ways of creating much better quality things like whistles and ocarinas and things like that. So I downloaded this from Thingiverse. It's just a regular whistle, but it has a little ball inside that will, make it trill, but it doesn't work very well. I can't get it to sound, and I think I've been reading about the whole intricacies of how the wind way crosses this thing called a fipple here, which is the thing that makes the sound itself, and then how the whole thing the cavity resonates. So one of the things I did is I took a recorder mouthpiece, and I tried to kind of mimic the design of this and created this 3D whistle here. It creates a nice tone. Still not optimal, I think. It's a little breathy sounding, and with it open it makes a much higher pitch, and you have to roll really loud to make it sound. But you can see the resolution of a 3D printer allows you to make very high quality, or I'd say pretty high quality, precision parts. So with that in mind, I started to look at the theory of whistles and wanting to build some models, some parametric models that let you create arbitrary tones in a predictable way. And I think ultimately like something like an ocarina, where you have 4 holes usually or more that you can cover to make the different parts of a scale. It's based on a concept called a Helmholtz resonator. And so I printed one of those things, or a couple of these. Helmholtz resonator is basically the most fundamental kind of a whistle. This has a air volume and then a escape tube. And when you excite the air over the top of this, it pressurizes and depressurizes with a characteristic resonant frequency, and it's based on the ratio of the area of this tube to the volume and length of the tube coming in, and the total volume of air inside here. So and if you decrease the volume by a factor of 4, you should get an octave higher frequency. And then finally a much smaller one. You notice that's a little flat because I think my equations are not precise. I'm not accounting for the volume of the air in the tube itself, so going to correct that. So anyway, I'm kind of off on this exploration of what is possible and to make some really high quality and open source musical instruments, and I hope you'll join our community and contribute some cool ideas and designs.